Okay, let's get started. Welcome to the afternoon session. It's my pleasure to introduce Professor Craig Kaplan. So he got his PhD in 2002 at the University of Washington.
That's correct.
And I made the mistake of opening up his PhD, which is on his website, and it's full of interesting stuff. So I'd recommend you do that. And since then, he's done various things, including some things at MoMath and whatnot. And currently, he's a professor at the University of Waterloo, which is, if you don't know, and you're not Canadian like me, it's like the MIT of Canada. An incredibly important institution.
MIT is the Waterloo of the U.S.
There you go. Okay. Very good, very good. Okay. So I won't say any more, but thank you very much. Take it away.
All right, thanks. Hi, everybody. Thanks for coming. It's just incredible to be here, to have been invited. I mean, it would have been weird if I had not been invited, I think, probably. But it's really just, this has been such an exciting year so far. The year has not gone the way I had initially planned, but of course it's better in so many ways. So I was involved in this discovery, in case that's not clear. And my job here is to give a more public account of what happened. So this is not really a math talk. If anything, it's more of a story of what happened, what has happened since November. Luckily, it's very easy to reconstruct the history of this discovery because this is not anything you would have known just from reading the paper or anything, but the whole thing happened by email. The four of us met virtually face-to-face. Like, we had our first Zoom meeting after we put the paper on the internet. So really everything happened by email. So I have a few scattered emails and then 2 or 3 just enormous threads with hundreds of messages each, which represent these papers. So a lot of what I'll show you is the story of how this happened, interspersed with some of our drawings and quotes. And of course, I will slip up once in a while and put some math in there too, show you what we did. The story begins way back in the bygone age of last November. So it starts here in November of 2022. I assume Dave doesn't want me to give his address or anything, but somewhere in East Yorkshire, David Smith was playing with polykites. Let me say just a little bit about Dave. So Dave is not a mathematician, not an academic. The storyline that we use in the press is Dave is a retired print technician. But he has a hobby, a passion for playing with geometry, just exploring the range of tilings that are possible from interesting shapes. So here's just one example off of his blog. And you can see that he picks some shape and then sees what are the different kinds of tilings I can make from that shape. Some of them are periodic, some of them are non-periodic. Those are both really interesting for different ways, for different reasons. And based on the talks this morning, hopefully you can recognize all the ones on the left are periodic, or rather are fragments of periodic tilings. And the one on the right presumably is meant to extend out radially with rotational symmetry, not translational symmetry. Now, I also use the word polykite, and this has come up a little bit already. Let me just expand on that briefly. Polyforms are an aspect of recreational mathematics and have been for decades, or possibly around a century, really. But they've been, the math of them has been experimented with and understood long before that. So polyominoes may be the most famous. If you glue together 4 squares, you get the Tetris pieces. 5 squares, you get pentominoes, which are a classic puzzle. Polyhexes are hexagons glued together. And polykites, no mystery there, they're just kites glued together. And as Sir Roger pointed out, this grid can be obtained by superimposing equilateral triangles and hexagons to get these kites, which are not the same as the kites in Penrose Kites and Darts, right? Different angles, different edge lengths, but also sort of the same general structure of a line of bilateral reflection. Polykites are a little bit more exotic in the polyform world, but they go back a ways. So here's something that came up in our conversation earlier. I mean, these are polygems, where each gem is a union of 2 kites. And this is an old web page by George Sickerman, about trying to build clusters of polygems that have bilateral symmetry. And you can see, for the problem he was studying, well, sure enough, right? The hat is hiding there in this web page that's about 10 years old and probably goes back a few years before that. So it's not like the shape itself was new. What we needed was someone to come along and say, hey, I wonder how this tiles the plane. So what Dave will often do is explore the different kinds of tilings he can make by drawing pictures digitally, or also by printing out, cutting out the shapes from paper and then just arranging them on a table. And I think this gets at something that's come up in the talks this morning about the relationship between mind and hand. So I think Dave would sympathize with what Marjorie was saying, and also Lucy in response to Natalie's talk this morning, right? That by engaging all your senses, by engaging your hands in working through the structure of this tiling, you can learn a lot. And it was through explorations of polykites that Dave came across a shape that was behaving strangely and sent me an email about it. So his first email was actually a couple of days before this, but it was a little more cagey. I think it was just noticing that I had recently published a paper about polyforms, and I'll say just a little bit about that in a minute. But this was the first time that I was given the privilege of seeing this shape, the hat, and that was on the 20th of November. And what Dave is saying here, it has a H number of at least 3. That's a way of saying it looks like you can build outward from a central tile quite a ways. We talked briefly about H numbers this morning, right? What Dave is saying to me is, I could take a hat, surround it by a layer of hats, surround that by a layer of hats, and surround that by a layer of hats. Makes it seem like you could build a tiling. But I couldn't figure out how to make it tile periodically. So in other words, the shape doesn't obviously tile the plane, but it also doesn't obviously not tile the plane. We're in some kind of twilight zone where we don't understand what's happening with this shape. And Dave is familiar with these mathematical topics, and it set off alarm bells. Like, something interesting is happening here. I have to figure this out. So that began our email exchange. And it was only a few days later that he finally said, look, could this potentially be a solution to the Einstein problem? Which, as you know, is one name for the question of whether there exists an aperiodic monotile. And with all modesty, he said, wouldn't that be a thing? Yeah, well, I think we now know QED, it was a thing, right? And I said, yeah, you've got my attention. In fact, my very first responses to Dave were something like, this looks really interesting, but I'm quite busy at the moment. And then when I saw this, I'm like, well, I guess I have to stop everything else I was doing and work on this full time now, which I more or less did modulo, like teaching the last lectures of the term up until about the first week of December. This was a puzzle that demanded to be worked out. So now, why was Dave contacting me in particular? Well, I have a long history playing around with tiling theory. My real research, most of my research is not so much about extending tiling theory itself, but about applying it in the context of computer graphics. So using tiling theory, the known parts of tiling theory, as a tool for making pretty pictures. And you mentioned my thesis earlier. So the escherization stuff was part of my PhD thesis about 20 years ago. This was, we've already used the word escherization a couple of times today. My paper was about an automated algorithm that you give it a shape that you want, and it will discover a shape that tiles the plane that's as close as possible to your shape. So it's kind of a computer-aided optimization system that figures out Escher-like tilings. And then more recently, but also in a continuous thread going back to those days, I'm really interested in tilings that evolve and change in space. But I'm also, in the process of doing that work, I became interested, fascinated by open problems in tiling theory, and occasionally would dip into that world a little bit too. And I'm particularly interested in Hayesh's problem, which is, we talked about Basic's example of a shape with Haesh number 6 this morning, and we don't know if there are any shapes with higher Haesh numbers. And more generally, we don't know if Haesh numbers go off to infinity or if there is some largest possible Haesh number in the plane. So it's really interesting to find shapes with high Haesh numbers. And I had written this paper that Dave first contacted me about that was published in late 2022, and that is concerned with using computation to figure out what the H numbers of polyforms are. So you have to do a lot of work, and you say, I figured it out. This particular polyhex has a H number of 4, and here is a demonstration of that fact, and I know for sure it doesn't have a H number of 5. And what Dave asked me was, can the software that I wrote for this project be adapted to work on kites, drafters or kites, but let's just focus on kites in particular. Luckily enough, about a year previously, I had worked with a very talented Waterloo undergrad on a summer research project, and she had added support for, actually support for polydrafters to my software, and every kite is just 2 drafters glued together. A drafter is a 30, 60, 90 magic triangle. So the hat is either 8 kites glued together or 16 drafters, which meant I could just describe the hat to my software and say, what is this shape's H number? And if my software came back and gave me a finite answer, if it said, I got to 4, I couldn't get to 5, for example, we'd be done, right? We would immediately be able to say, the H number is 4, it doesn't tile the plane. But I said to my software, is the H number 4? It said, yeah, it's at least 4. Is it at least 5? Yes, it's at least 5. Is it at least 10? The software's like, well, yeah, here, look, it's at least 10. It might be higher, I don't know. The software can't tell if it goes off to infinity, but it can at least provide proof that it's 10 or higher by giving you 10 coronas. And so I said, well, here it is. I mean, this is not slowing down at all. This is really interesting. Something's happening here. Right, already, in terms of mathematical discovery, either this shape tiles the plane in a really mysterious way we haven't figured out yet, or it doesn't tile the plane and it blows away the previous record for H numbers. That would be cool, right? The record is 6. If I could just say this thing is 10, I would have been very happy already. This, by the way, we were talking about deceptions and patches that can't be extended. You can see, like, this patch can't be extended, right? Like, there are these nooks that definitely can't be filled in by more hats. So here's an example of, I can build outward as far as I want, but not necessarily in a way that can be extended to a tiling of the plane. Okay, so the computer has generated this patch by basically brute force. It doesn't know anything about the underlying nature of how this shape tiles the plane. So what do we do, right? How do we use this information? We don't know that this extends to a tiling of the plane, but let's optimistically assume that it does. Is it completely orderly? Well, it doesn't look like it. Is it completely random? Doesn't look like that either. So if you make the optimistic assumption that there's some structure to be found here, the next step is to go off and look for it, right? Where is the structure? What is it? And, if you're a non-mathematician, I'm happy to tell you, you're about to do math, but the good news is that doesn't have to mean you're scribbling walls full of equations onto whiteboards or adding up long sums or anything like that. In this case, doing the math means coloring in the tiles. Just coloring, right? Trying to find patterns, trying to find structure, trying to account for why the tiles are behaving the way they do. And you can see that there is behavior here. It's not random. Even going back to Dave's paper cutouts, he had the presence of mind to notice that the reflected hats are behaving a little bit special, right? They're not just anywhere. They're in some kind of sparse distribution. And so he cut them out of a separate color paper, which was great because it's there's something going on there. And you can see that reproduced here in our colorings. The computer, through brute force search, also was somehow constrained to putting those reflected hats where they were. That can't be a coincidence. That's got to mean something, right? And so we started saying, well, there are these long chains that flow in different directions, and there are these large regions with threefold rotational symmetry. What does it all mean? That was the 25th and the 26th of November. And then also separately, we came upon the same coloring at around the same time, and more or less our emails crossed in the air, of coloring in the reflected tiles in one color and then noticing that every reflected tile has the same little cluster of neighbors around it. This is what at the time I called it a little cyst, because it's like the reflected tile is covered by this cocoon sort of thing. And that those 4 tile chunks, those small patches, themselves had this interesting orderly arrangement that suggested there was more to be found. And so at that point, I'm like, yeah, I think we're on the right track here. We have to keep looking at this. So, as I said to Dave, if you want to believe that this is an aperiodic monotile, what do you have to do? What are you trying to show about it? Well, the first thing you have to show is that it tiles the plane. That we didn't just get lucky and find this giant patch, but that there's some rule that tells you how to go to infinity. And you have to find out what that rule is. So how do you do that, right? This is a very different process from a lot of the other aperiodic tile sets that we have historically. Berger's set and then Robinson's and so on, they were like manufactured, right? They were created in the math factory where you say, well, I really need a tile set with these properties. And they glued on the properties in the right places to get the tiling they wanted. Whereas this thing, well, it was discovered in the wild, right? It was like you found a weird mushroom under a rock and you had to, it wouldn't be under a rock, I guess. You found a weird mushroom in the forest and you had to figure out why it behaved the way it did. So we had to work with the data we had rather than kind of manipulating it to have the properties we wanted. So the nice part of that is the software I was using here gave us lots of data, gave us these big chunks of tiles that we could study in the search for patterns. And here's one strategy that you might be able to use, right? You sort of say, well, there's some kind of analogy going on here where the 4 tile unit here, if I can find it, the 4 tile unit here, kind of looks like this structure over here, where maybe each of those light blue tiles is expanded into a copy of the 4 tile unit. And maybe that analogy continues into this larger thing that's made out of 3 of those structures and 1 additional 4 tile unit in the middle, right? Something like that. Maybe those 3 levels, if we assume that we've generated enough data that multiple levels of some hypothetical substitution system are on display in the data, maybe we can reverse engineer what those substitution rules must have been, or a set of substitution rules that account for everything that you're seeing. And that's the direction we went in. So a few days, maybe a week after that, on my birthday, on my 50th birthday, so as my present to myself, I said, I finally figured something out. I was hoping the tile would, give me a present today, and it did. This is not the substitution system that we ended up with, but it is a set of rules that if you iterate them, here I give you the evidence that, I can fill a large region with copies of these shapes, which then can be turned back into hats if you really needed to, although I'm not demonstrating that here. And then after a bunch of refinement, so I guess another week after that, I had started to head in the direction of these things that we now call metatiles, sort of a different way to group the tiles together into clusters that turned out to be productive for coming up with the proof. So you can see up there I've got those 4 tiles together. That was always the key for me. It was like, okay, that I take as given. Like that's my axiom. I want that cluster of tiles to always be together. What else do I need to do to account for all the other tiles in the tiling? And you can see like the individual hats are mostly abstracted away as noise, and now we're operating at the level of the metatiles. But what I kept discovering was, well, the larger red tiles, which are supposed to kind of symbolically represent grouping the metatiles together and moving up a level in this hierarchy that you've seen a couple of times today, they look right, but they never line up exactly with the metatiles themselves. You can't just sort of you can't take this black tiling, scale it up, and maybe rotate it or something, and it becomes the red tiling. It's always a little bit off. And that really bothered me because all the substitution tilings I knew about had that property. They were always rigid in this geometric way where you just can scale up and put in new tiles. And eventually the good news was I realized, Chaim disabused me of the necessity of that, right? Like, that doesn't have to happen. It doesn't need to be geometrically rigid. for you to have a working substitution system. So eventually we really just used this system as is. We had this propeller-shaped tile initially, which I mistakenly called a Philfot, even though a Philfot should have 4 arms, and that we later renamed a Triskelion, which is way cooler name anyway. And I love the flag of the Isle of Man, so I'm happy to call it a Triskelion with the 3 legs. Okay, so we came up with something like this. Joseph later refined this a little bit. He didn't like that I had 3 arms there that were really all kind of symmetric copies of each other, so he pared that down to just like 1 propeller blade. But now we arrive at the actual metatiles that we use in the paper. So we say every tiling by hats, well, we're not at the stage of talking about every tiling by hats. We're talking about how do we build a tiling by hats. Well, we say if you start with these 4 clusters and give each cluster, each of those shapes, H, T, P, and F, a rule that replaces it by smaller copies of H, T, P, and F, more or less, then you can iterate those rules and build larger and larger patches of hats. And in the limit, you're allowed to say that you can tile the plane with hats. Now, that in the limit hides some pretty sophisticated mathematics and a kind of magic trick. This came up this morning. Being able to say that I can make an arbitrarily large finite patch is not necessarily the same thing as saying I can tile the plane, but we have some really powerful theorems in tiling theory that say that, yeah, most of the time that is a fair thing to say, that you can squint and imagine iterating these rules infinitely many times, and you get a tiling that's infinitely big. That's not obvious, but it happens to be true. Somebody who was interviewing me asked, does that theorem have a really cool name that I can quote? And I was like, as far as I know, it's called Theorem 3.7.1, right, out of Grunbaum and Shepard. I don't think it has a cooler name than that. That's a pretty cool name, don't get me wrong. But yeah, if it has another name, I don't know. And so using those rules, you can like take one of those H's that has 4 hats in it and apply the rules, and you get, what is that, like 3 H's and a T and 3 F's and 3 P's, all contained inside a larger H. And then you apply the same rule again, the same construction, you get an even larger thing and an even larger thing, and hypothetically you can continue that process as many times as you like to get a tiling of the plane. And so as I said to Dave, as early as December 2nd, I guess still my birthday, when I had that first substitution system, I said, if your goal is to solve the Einstein problem, if you're trying to find an aperiodic monotile, this is halfway, right? Because we know that we have a shape that tiles the plane. We have a monotile. We've solved the monotile problem. But we don't know that the monotile is aperiodic. And so what's the other half of that question? What other thing do we need to prove? Well, we know that we have a substitution that happens to produce a non-periodic tiling. But you have to turn that around as well. You have to say, if I have any tiling by hats, it must be non-periodic. In other words, if I kind of cover my eyes and someone hands me a fully formed tiling by hats, for which I had no control over the construction, I can still show you why it has to be non-periodic. And that undoubtedly is the harder direction of any kind of proof of aperiodicity, right? This is a very forward thing where I say, here are some rules, use them, and you get a tiling. Great, done. But here we have to deal with the potential of tilings that we had no control over. And in some sense, we have to account for not just any one tiling that we produced, but hypothetically, the space of all possible tilings that might exist from the hat. And we have to constrain them just enough, mathematically, to say no periodicity allowed. So that is the hard part. And, in a way, that's the point where I reach the limit of my mathematical ability. I'm not really a mathematician. I'm more of a computer scientist. Those are, in some sense, there's a big overlap. And at Waterloo, in fact, computer scientists are all in the math faculty, so we are mathematicians. But I don't prove things for a living. So I could dream up this construction, but the side of the proof where we say, and by the way, every tiling must be non-periodic, it's like, yeah, I don't know that I'm going to be able to do that. We're going to need some help. So at this point in December, it was time to think about calling in reinforcements. But not quite yet. And I shamefully admit the next bit here. So there's a little bit of an intermission here in December. First of all, I begged Dave for more time. I was like, as soon as we bring in other mathematicians, this is going to be over too fast, right? I shall have to duel him left-handed. Use the right, it's over too quick. So I knew it was going to be over too fast. So please give me a little bit more time. Don't worry about being scooped here. Only some weirdo would work on tiling theory over the holidays, which I did. And Dave very kindly said, please keep going. And also very presciently said, it'd be really good to publish this in March 2023. I was like, I'll see what I can do, I thought. And sure enough, QED again. Slightly more intermission, by the way. Dave said, what do you think it looks like, by the way? This was on December 5th. A t-shirt, bird in flight, some boot, some weird fish. And I told my family, and they said, well, it looks like a shirt, maybe a hat. The hat stuck. You can see whatever. There's no rule that it has to be a hat. If you want to see a shirt, you can see a shirt. That's fine. I thought hat was a little bit easier to read and write in an academic paper. That's really the only reason to call it a hat in a paper. So as I said to Dave, please give me until New Year's Eve, and then in the new year, we'll immediately email reinforcements. And that's what we did. On January 2nd, I emailed Chaim Goodman-Strauss, and I said, something interesting just happened. Well, I gave him more detail than that. I said, Dave found what looks like an aperiodic monotile. Do you want, join our team, right? I'd like to add you to my LinkedIn network or something. I knew Chaim from way back. I don't even know when we first met, but it was undoubtedly at something like the Gathering for Gardner events. And I've met him. I crossed paths with him a couple of times at tiling theory conferences. And he was my go-to guy for sort of tying together the state of modern tiling theory. I always love that diagram up at the top that sort of neatly summarizes the relationships between the different problems at the intersection of tilings and computation. And that was always an inspiration to me, sort of thinking about what problems I would want to study. And he also came up with this now well-known trilobite and crab tiling, which, by the way, there really are not a lot of aperiodic sets of size 2, right? We don't have a lot of aperiodic sets overall in some sense, and there are very few sets of size 2. So to be part of that collection is already a pretty big deal. And we also don't have a lot of sets of size 1, I'll have you know. So I emailed Chaim. In the meantime, about 2 weeks. Oh, and by the way, as Cindy was saying, Chaim wrote back saying, I'm in the middle of changing jobs. My time is a little bit weird. So, he provided a lot of mathematical support and moral support, and also, why are you not already emailing Joseph support? So very soon after, we emailed Joseph Myers. Now, I have known of Joseph's work. I don't even know, again, how long I've known this work. I cite it in my PhD, which is 2002, and he had already been working on it for a few years back then. So I was familiar with his work doing computation to study the tiling theoretic properties of polyforms. So there's a random table that you don't have to care about here. I think the first time I met Chaim, he was carrying around laser-cut wooden pieces of Joseph's record-holding 10 anisahedral 16 hex, which, you can make this tile the plane, but it's very, very complicated to see how. And maybe that's all I'll say about that. But yeah, Joseph was ideally positioned to be involved in this work because, of course, the hat is a polykite. So, he had all this incredible software for studying polyforms for their tiling properties. He wasn't doing polykites, but in some sense, he had all the expertise one would hope for to apply to this problem. Now, as Chaim and I had said, even before reaching out to Joseph, we could both see, to do this proof, all you're going to have to do is, do this kind of exhaustive system of cases, basically studying all the ways hats might fit together to eliminate the ways that could possibly lead to periodicity, right? And it's just basically a huge number of cases of examining, as you saw in the proof of Robinson's tiling that Natalie gave in the first talk this morning, right? you say, well, if you put a tile like this, then you're forced to have these around it. And then those are forced to group together like this. And those are forced to group together in the following way. And you just keep doing that out to infinity until you can say, therefore, this tiling can't be periodic. Because of the reasons we kind of heard this morning. If you assume it was periodic, then there's a hypothetical arrow along which the tiling repeats. But I will point at a part of the tiling with a structure so large that it can't possibly repeat with the arrow that you gave me. And we don't need to say it in more detail than that. But like, as I said, Robinson's tiles were engineered to do that. He picked all the rules that accounted for their structure. We don't have that luxury. We have to work with the tile we're given. And because we're only dealing with a single shape, it's fair to assume that the ways that it's going to fit together are going to have to be more convoluted. When you have more shapes, you can more tightly control how they can be neighbors with each other and still end up with an infinite tiling. With a single shape, that shape's going to have to be more flexible, but not too flexible because then you're going to allow periodicity. Oops. So how do we figure that out? Well, the answer turns out to be you email Joseph, you sort of order up the proof, and then a week later he sends it to you. So I highly recommend it, right? So it wasn't actually a week, right? It was actually 8 days. We did a fact-checking interview with Quantum Magazine where they said, oh yeah, and it says here that it took you a week to come up with the proof. And Joseph's just like, no, 8 days, right? Like, let's not exaggerate here. And so Joseph worked out the other direction of the proof, as I was saying, that if you give me a tiling by hats, I can prove that it can't possibly be periodic. So let me say just a little bit about how that might work without going too much over time. All right. First and foremost, I will say, you notice that Joseph's comment here says, if none of the software has soundness affecting bugs, and there are no mistakes in the hand parts of the proof. So what he's hinting at here is that this is a proof that uses both mathematics and computing, right? We might call it a computer-assisted proof. Joseph and I both had software that could help to analyze these shapes, and that software turned out to play a crucial role in doing the bookkeeping on that explosion of combinatorial cases that you need to consider when trying to understand the behavior of hat tilings. So how did that work? Well, let me just introduce a very simple mathematical idea. This is sort of like, coming out of the world of Hessian numbers. I will say a two-patch is a shape surrounded by copies of itself, surrounded by another layer of copies of itself. Great. And there's only so many ways that a hat can be a neighbor with another hat. So in fact, there's only so many distinct two-patches that could possibly exist. And you could write a computer program to enumerate all of them. But not all of them are interesting. I thought I gave myself a laser pointer here. Not all of them are interesting. Like, for example, here we have a pocket that cannot possibly be filled by another hat. There's another one. So I kind of don't need to consider this particular two-patch very deeply because I know this two-patch cannot possibly occur in a tiling of the plane. It has these unfillable holes, so if you just give me a tiling, you don't need to look for that two-patch because it would definitely have a hole in the tiling if you try to use it. You have holes that can't be filled. So I refine my definition. I talk about a surroundable two-patch as being a two-patch that lives inside a three-patch, or a two-patch that has the capability of being surrounded. And once again, you can enumerate all of these, right? The way I did it, which is pretty easy, is enumerate all the three patches and then just identify all the unique two patches within them. Because there will be this two patch will have multiple ways to be surrounded a third time. I don't care about the differences between those ways. I just want the two patch itself. But I will refer to those as surroundable two patches. Now, in principle, you could do this all by hand. But you wouldn't want to. We have software. We don't mind enumerating them. And the good news is, there's not even that many. There's 188. I can just about imagine, in an earlier century, somebody without computers figuring all of these out and then working through, like Kepler would have figured these all out and worked out the proof. But of course, we're perfectly happy to use software to augment our brute force abilities here. So enumerate the 188 surroundable 2 patches, and then, this was something that Joseph did, figure out a unique, like a deterministic way to label all the tiles in the middle of that 2 patch, so the inner tile and the layer around it, deterministically with the features of the metatiles that we already knew we wanted to exist. In other words, Joseph showed, through computation, that no matter what tiling you're able to produce made out of hats, it must be viewable as a tiling by metatiles. You must be able to kind of take a step back and reverse engineer the positions of all those metatiles and the identities of the hats within them. So that's a good first step, right? We've done kind of a level of grouping to say every tile by hats is necessarily a tiling by metatiles. But we're not done yet, because the metatiles could tile periodically, who knows? We really need like an infinite number of layers of hierarchy above the hats. So the next step is to show that the metatiles can only cluster together in the ways that we want. And this is kind of just a choose-your-own-adventure comic, right? We say, if you, I'm really eliding it in these slides, but if you start with one of these, you're forced immediately to get this. That's not too hard to see. Then you have these 3 positions where you have to make a choice. And if you choose to do this, then you're left with this position where you have to make a choice. And if you fill it the wrong way, you come around here. All of these are forced in sequence. And you get to this point here, which in the paper we say, if you ever get this configuration of 2 parallelograms, there's nothing you can put here to complete a tiling of the plane. So this can't arise. So if you get here, you have to make this choice, put one of these F's here, and then lo and behold, you complete this very attractive looking blob of metatiles, which, if you kind of edit in the right way that I won't go into, you end up with something that it's not geometrically identical to H, but we say it's combinatorially equivalent to H, which means in a tiling by metatiles, it plays, this cluster of metatiles plays the role of H in another tiling. And what that means is you could take your hats, group them together into metatiles, and then group the metatiles together into larger metatiles, which we call supertiles, super metatiles. I don't know. And then, but now the cool part about that step is that would just give you another tiling of the plane by metatiles, which is subject to the same grouping, because that big H has the correct combinatorial behavior. And you could take that larger tiling and group them together into an even larger tiling. And you can just apply basically this choose-your-own-adventure system of rules to reverse engineer not just one layer of supertiles above the metatiles, but infinitely many layers. And that's the last thing you need, right? That infinite hierarchy of supertiles to say QED, right? Like, we know that the hat tiles the plane because we have a substitution system that gives us the tiling. And from the work that Joseph did, first grouping hats into clusters, and then grouping those metatiles into supertiles through infinitely many levels, we now know that for any tiling by hats, there must exist a uniquely determined hierarchy of supertiles above it. And for the reasons that we talked about this morning that we're kind of glossing over here, that unique hierarchy guarantees that the tiling has to be non-periodic. So we have tilings, and they must be non-periodic. Therefore, the hat is an aperiodic monotile. Good news. And indeed, if that had been it, if that had been the whole story, we would probably still be here today, right? I mean, that's great. That's a real breakthrough mathematically that we can all be incredibly excited about. If I had seen this out in the wild, I would have been tremendously excited about it. To be involved in it is just another level of amazing. But that could have been enough. I keep thinking of the song Dayenu from the Passover Seder. Like, if that had been all we done, then Dayenu, right? It would have been enough for us. Anyway, okay. I'm glad you got it. It's not just me. All right. That would have been enough. But it's not. We're not done, right? I've got a few more things to show you. we're not done because, right? Let's rewind the clock to December. Because back in December, David Smith was still playing with polykites. He wasn't done. He had a few more tricks to play on us. So back in December, while I was frantically trying to come up with a substitution system, Dave emailed me on December 6th to say, oh, by the way, sorry, just one more question. Sorry about this. Probably not the right time. I really appreciate that, Dave. It's very Canadian, right? Like, oh, sorry to bother you. I came across another polykite of interest, a modified hat. So he had come up, this is a 10 kite. In this case, I guess it's drawn as 20 drafters. A 10 kite that we now call the turtle. That's upside down, but maybe you can see a turtle shape over there with the head kind of sticking up and the two legs. That's kind of, like, I didn't know that I was subscribing to the monotile of the month club, right? Like, that's kind of but I mean, think about how you would react, right? We had a 50-year dry spell, no aperiodic monotiles, and then now there's two. That seem different from each other within a span of a few weeks. That is pretty mind-blowing. I basically, that exploded my brain. I kind of said, that looks cool. Let me just put that to the side. I've got to work on this hat thing. I really won't be able to do both of these at the same time. Although, it gave off every indication of behaving like the hat, which is kind of wild. So, really, Joseph picked up the thread here. After he was done revolutionizing tiling theory, he said, well, let me look at that turtle thing. That seems interesting, too. So he said, okay, I added polykite support to his software. So now he could plug in hats and turtles and see what they did in terms of tiling theory. And that was on January 29th. And a week after that, he said, okay, well, that's interesting. It turns out, like, in adding polykite support to his software, it allowed him to compute like numbers of patches of different sizes for the hat and the turtle, and the different configurations that they could produce. And he saw the numbers always lined up, right? Hats always did the same thing as turtles and vice versa. That's a strong clue. Like, these things have to be connected. And eventually he saw the connection. He said, okay, not only is tile B, the turtle, periodic, in fact, if you draw a line through the hat and the turtle, they yield an infinite continuum of shapes that are all aperiodic. And then, in fact, all tile the same way. And the best demonstration that they all tile the same way is just, you almost can just say QED at this point, right? Like, this just makes it so visceral that these are all within one continuous family. It need not have been the case in some sense that you could animate through the space of tilings continuously, although now there's every reason to understand why that would have to be the case. And then even more stunning than that, Joseph came back about a couple of weeks later and said, not only are the hat and the turtle connected in this continuum, but it seems like that continuum itself gives you a basis for a second proof of aperiodicity. That really blew my mind, and I think the rest of the team as well. Now, this one's much harder to explain, so I more or less won't. I'll just say, the core of this proof is to say, if you suppose, by way of contradiction, suppose it was periodic, and you had a periodic tiling by hats, then you could move the slider all the way to one end of that continuum and get this equivalent periodic tiling by these shapes that we call chevrons, and move the slider all the way to the other end of the continuum and get another equivalent tiling by these shapes that we call comets. And now the interesting thing here is that both chevrons and comets are not polykites, but polyimines. They can be constructed as the unions of equilateral triangles. And it turns out that you could basically say, if this was periodic, then you definitely would have these two tilings, and they would both be periodic as well. But then you can say, but therefore, these two underlying equilateral triangle tilings would have to be related in a particular way. It would have to be sort of a uniform scaling, one of the other. But then you can show with a little bit more work that uniform scaling is impossible. that uniform scaling could not exist. Because we know how many comets would have to live in that box, we know how many shepherds would have to live in that box, and because of that, we know how much you would have to scale by, and then you can say that scale factor would have to be impossible because it's not compatible with, more or less, with the square roots of 3 that permeate the triangular tiling. Maybe that's enough. So we threw that extra proof, bonus proof, 2 for 1, into the first paper. That became our first paper, an aperiodic monotile, which we released on March 20th. And as Marjorie said, it really took off online, which is just awesome, incredibly wonderful thing to see. People got really excited about exploring what you could do with it aesthetically. You can see some examples of that out in the hall, which I love. Here are a few that I've collected from the internet. So very early on, we had some quilting, and there's another really beautiful quilt outside here that I hadn't seen before. John Paul Wheatley is a professional soccer ball designer. Football. I said that wrong here. And he noticed, so in fact, early on, Dave had experimented with hats and hexagons. It's very easy to make periodic tilings of the plane out of hats and regular hexagons together. And John Paul just said, well, what if the hexagon were a pentagon? And very naturally, everything just works out. The pentagon takes away or adds some curvature, positive curvature, and forces that periodic tiling of the plane to fold up into a ball, basically. And you get this thing with the dodecahedral symmetry. Yoshi has been doing all kinds of amazing Escher-like tilings out of our shapes. Love it. You saw his kind of ghost-like spectre in Marjorie's talk this morning. And this I discovered only a couple of days ago. Late last week, someone tweeted saying, is this the aperiodic monotile? And yeah, sure enough. First of all, very interesting that you can take patches. There exist infinite strips of the tiling that do repeat in one dimension. You can't do that at any height you want, but you can build some infinite strips. And if they repeat in one dimension, then you can wrap that direction around a cylinder. And if you can do that, you can make beer, which is outstanding. So we got beer and football together on with hats. I mean, you've got to have a game where you drink that beer. Now, I don't know what the story is. We contacted them, the White Hag. They're in County Sligo in Ireland. And hang on a second, we contacted them, and they said, we have a few left, we'll send them to you. So hopefully we're going to be toasting with White Hag beer soon. Yeah, Stefan, do you have a question?
Great. Did you find a way to attach the cans to the head?
Oh, we need someone has the big felt hat. We've got to have the 2 beer cans on it. Fantastic. Yeah, that'd be great. Yeah, that's amazing. I mean, yeah, we're very happy with all the things people have been doing with the hat. Okay, I got a couple more. We're not quite done. There's a few more steps here. As Marjorie was saying, when people put out candidate aperiodic monotiles, inevitably someone says, oh yeah, that's cool, but it's not what we wanted. And again, the answer is you didn't tell me what you wanted. You didn't give me what the rules were. For my part, I will say, I am completely satisfied with hats and turtles and all that. You can object. You can say, it's not what I wanted because it uses both hats and reflected hats. If you had asked me up until last November, you said, if you had asked me whether I would point at a tiling like this and say, this is absolutely a solution to the Einstein problem, I would have no problem saying, yeah, of course. Yeah, it has to be. Mathematically, if you look at Grunbaum and Shepard, which is about as authoritative a reference as you could hope for tiling theory, when they describe what a monohedral tiling is, a tiling by one shape, they say, yeah, you can reflect. I mean, it says specifically, copies of a tile that are put into place by translation, rotation, and reflection. So great. This is a solution to the Einstein problem. But some people did say it's not what we wanted because I don't think of a shape and its mirror image as being the same. Now, so there's a little bit of tension there. But that's great. As mathematicians, we love this stuff because we can say, oh yeah, you're right. I'm still satisfied with the solution to the original Einstein problem, but what you're saying is, here's a slight variation on the problem that is also really interesting. So part of the objection is legitimate. It's on the basis of physical objects that we're used to working with every day. If I were to manufacture hats out of ceramic and glaze them, I can't just flip a hat over and put it in my floor, right? I get a shape that is the reflection of the original hat, but it doesn't have the same affordances. It doesn't work the same. So I can, although I can get the reflected shape, it doesn't behave the same way. And certainly, we think of a left shoe and a right shoe as being kind of the same form in space, but they're definitely not interchangeable. And if you think they are, I encourage you to try walking around with your shoes on the wrong feet, right? So there's a natural follow-up question here, which is there an aperiodic monotile that tiles the plane but doesn't need to use reflections? And I should say, you can almost ask an unlimited number of variations of this question. A natural one to ask at this point is there an aperiodic monotile that only uses translations, where every tile is just slid around without ever rotating or reflecting? Now, we know that in the two-dimensional plane there is not. So, in fact, we do know, this is an old result, that if you can tile the plane with copies of a shape by translation alone, then you can tile periodically with that shape. And we now know also, as of late last year, that in sufficiently high dimensions, there exist translational aperiodic monotiles, where sufficiently high is so high that I don't even know how many dimensions you need. It's a very high number. I believe that we're going to get a talk about this tomorrow, right, by Rachel Greenfeld, who may or may not be here. Yeah, okay, great. Cool. I look forward to it. It's a really cool result in a more difficult to visualize part of tiling theory, because it's infinity googly dimensions that I don't even know how many. So this produced an interesting tension, a new period of exploration and study of this new question of whether there could exist an aperiodic monotile that didn't use reflections. And so we all settled in for the long wait for somebody to come up with the answer. And it took a whole 5 days. It was very uncomfortable. It was 5 days, 6 days. It wasn't easy, but somehow we fought the good fight. We're all here together. So in March 2023, David had one more trick up his sleeve. I'm sure he has more tricks up his sleeve, but he had one more trick apropos to this talk, which is he noticed that Yoshi was doing something interesting with a shape that we only had called tile 1-1. Now, tile 1-1 is the midpoint of this continuum that Joseph had found, and it's an equilateral polygon. All its edges have the same length. If you will allow me to call this one long edge two short edges side by side, which hopefully you will. Now, Joseph observed in the first paper, tile 1-1 tiles periodically. And so basically, in the context of our first paper, we just put it on the reject pile. It's equilateral, so it supports more adjacencies. So, because it has a little bit more flexibility, it just happens to allow periodic tilings. Oh well. But David just got to wondering. Well, hold on. Have you seen this tile? It's kind of cool. It's right in the middle of the evolutionary scale. And, he asked, can tile 1-1 tile periodically without reflections? If not, I think it needs more attention. We should be looking at this. And of course I said, ha, no way. Or at least, it seems so unlikely to me. Just like too good of a coincidence, right? Too good to be true. There's no way that a non-reflective chiral, whatever you want to call it, that shape was hiding there inside of our continuum. But sure enough, we kept playing. And, David produced larger and larger patches working by hand. He said we should call it the Spectre, which is great. And so we started to basically play out the same routine, the same playbook, saying, all right, let's study this and see if it is an aperiodic monotile if you disallow reflections. So the first problem here is this shape is not a polyform, which is kind of depressing. Polyforms are nice because they let you do a lot of computation discretely on a discrete grid out of little units. And that's nice computationally. It's just nice to write software in a discrete world. But I despaired of trying to do equivalent software with this shape because it's not a polyform. Happily, Joseph, again, had this amazing insight. It's like, hold on a second. A tiling by tile 1-1 is equivalent to a tiling by hats and turtles. And you can see that here. Again, just kind of an amazing insight that came out of nowhere and solves exactly the problem we were trying to solve. And so that means that if I want to generate large patches of tile 1-1, all I have to do is generate a large patch of hats and turtles together, and then I can kind of morph it into a tiling by tile 1-1. Wow. And so that's what we started to do. Once again, let's make lots of data so that we can study this thing. So I adapted my software, won't go into the details, and made large patches, and then we did the same thing. We started to color them in. This time, Chaim got to get in more on the coloring action, which is great. So we started saying, well, let's look for structures, and he found a bunch here. Eventually, I found this coloring, which shows that copies of tile 1 group nicely into these blobs that repeat. So this is really interesting. It's like, wait a second. The whole thing can be grouped into only 2 kinds of blobs, 2 kinds of patches. That's got to be significant somehow. So that became a starting point for our study. And as Chaim pointed out, these blobs are kind of combinatorially equivalent to a tiling by regular hexagons. Each one has 6 neighbors, and they meet 3 at every shared vertex. So maybe you can study these just by studying those hexagons and the way they meet. And that's what we started to do. Joseph started to produce these amazing diagrams showing that, there are exactly 9 types of marked hexagon, and they have this particular arrangement. And here's one sample. I wrote some code to generate larger patches of those marked hexagons. And now, tile 1-1 almost doesn't matter, because it's let's just play with these hexagons and study them. And you can, just by changing the colors of the individual hexagons, you can start to bring out all kinds of wonderful structures lurking in this tiling. And Chaim, you can see here, is starting to color it in, looking for repeating structures. Eventually, I came up with a different set of substitution rules that work through those 2 blobs from earlier that use those 2 blobs and give a rule that uses each and backs up a step and works from this separate shape that is 2 copies of tile 1-1 glued together that we now call a mystic, and that to all of us, I think, looked unmistakably like a Buddha in meditation. So that was really cool too. And the key, the secret sauce that made these substitution rules work is that at every step, you have to flip all the tiles over together. That was really weird. It's great, because it means the whole thing stays one-sided. Within each of these patches, the individual tiles are all the same orientation. They're all, either all mirror images or all not. But each iteration of the substitution takes you from one to the other. And that last little piece of the puzzle allowed Joseph to take his hexagons and do the usual proof that says that the grouping of hexagons into larger supertiles is forced, like the way we talked about before, that you can build this infinite hierarchy on top of individual tiles. And that was enough to complete the proof that that tile 1-1, if you don't allow yourself to use reflections, tiles aperiodically, is an aperiodic monotile. And that was on the 11th of April. We just had to do one more thing, and it's an easy modification. You say, well, hold on. You haven't really solved the problem because tile 1-1 allowed periodic tilings. So sure, you could say that you're choosing not to use reflections, but you're not forced not to use reflections. That's true, but we also show, and this is the easy step relatively speaking, that there are lots of ways that you can modify the edges of tile 1-1 so that no tile can ever be adjacent to its mirror image. I always do this, but of course it should be this because my hands are already mirror images. So that a shape and its mirror image can never be side by side. Yeah, that's weird. And Dave has some sketches of all sorts of possible modifications there. So that was our second result, and that paper appeared, I think it was May 29th, just before I went off to give a talk about this stuff, so that worked out well. And again, people have been doing all kinds of wonderful experiments. There's another tiling by Yoshi, very natural kind of elephant shape. And Robert Fathauer said, well, if you're going to call it the Spectre, I'm going to necessarily draw ghosts, and rightly so. I feel like I should leave off with just a couple of random observations. So let me just say a few high-level things here. This was an incredible period of discovery for me, and I hope for my collaborators. Completely unlikely. Like if grad students are in the audience, they're like, ooh, how do you achieve a discovery like this? I have no idea, right? Like this thing, as far as my perspective goes, this thing fell out of the sky, and all I had to do was kind of go, whoa, catch it, right, before I lose it. And, in some ways, all of the people who worked on this paper had been mentally and psychologically preparing themselves for this kind of development, this kind of discovery, if only we had known where to look. And it was really good luck that Dave stumbled upon the shape that he did and got us that last step down to a monotile. I will say, yeah, it's another incredible achievement. And I mean, absolutely, amateur, I think, is a word that has become a little benighted maybe in the last few years. There are negative associations with it, but I don't mean any of those. I mean this in the best, most positive sense of someone who loves a subject and pursues it for its own sake. And there is this interesting history that we don't have time to go into of discoveries in tiling theory by amateurs that has enriched the field tremendously. I think part of that is due to the fact that tiling theory is accessible, and it's something that you can get your hands on as well as your eyes and your mind. And that's done a lot of good for the field. Maybe a bit of a challenge to the assumptions about aperiodicity. If you had asked us before this work was done, as Chaim said in his quote, right, aperiodicity seemed really hard. Maybe it seems a little bit less hard now because such a simple shape has achieved it. And maybe we'll find other ways that the hat changes the way we think about how hard aperiodicity is as a phenomenon. And of course, it's a reminder of just how much wonderful stuff there is left to look at in tiling theory. And I'm still excited about pursuing the subject. We're very much not done. So I'll leave off there. I want to thank Joel for desecrating his flesh with our work. You can find me there, and I'm happy to answer questions if we have time. Thanks. Not me. Thank you.
All right, let's have some questions.
Do we have time?
Yeah.
Go ahead. Oh, sorry, I shouldn't. Yeah, I'm not in charge. I'll just answer.
That was just awesome. Thank you so much for that lovely talk. I have so many questions, but let me just choose this one. So by the end of November, you've got three possibilities. You've got an aperiodic monotile. You've got a new Heesh number world record, both of which amazing. Or it turns out to tile periodic.
That's right,
which
yeah.
I guess would have been a bit disappointing. So how surprised were you? Would you have been at each stage if it had turned out
yeah.
to tile periodic?
That's a little bit in our email chain. So that's a great question. To repeat, going back to, I won't go back. Going back to Dave's early emails to me, he said it has a H number of at least 3. I couldn't get to tile periodically. So it might have been a non-tiler with a high H number. It might have been a tiler, a periodic tiler with a high period number, or we would say isohedral number, something we don't need to get into. Or it might have been an aperiodic monotile. After having played with the hat, even for just a couple of days, so by November 24th, 25th, I was basically certain it tiled the plane. Because I had these huge patches. The chances that it could get out to 10, 12, 16 coronas and not tile, that was, Occam's razor at that point kicked in, like, forget it, it's got to tile the plane. But as I even, in those emails to Dave, I said, I definitely won't rule out that it's periodic. It might be periodic, and we just haven't found the right cluster of tiles to make it tile periodically yet. And unfortunately for me, right, I don't have software that can check that out to some bound. That's Joseph's software. So I knew that when we contacted Joseph, he'd be able to figure it out. But I didn't have the means to try to check that myself. So I just maintained the hope that it was an aperiodic monotile and continued to explore. I mean, also, if you look at some of those computer-generated patches, Okay, I will go back for that. It's going to be slow, though. Hang on just a second. Where am I? Hopefully it's not too long-winded an answer, too. If you go back to like this drawing, the computer, in some sense, is parsimonious. It does the least amount of work to get things to fit together. So the fact that it was lazy and did as little as possible and still was forced to produce this structure is very telling, right? It's like, yeah, there's, at that point I thought it's probably aperiodic. I believe in my email to Chaim saying join our team, I said, I'm 99.9% sure it tiles the plane and 90% sure it tiles aperiodically. So that's about where I was. Yeah, I'll stop there.
Okay, another couple questions?
Yeah. I see one up here.
Yeah, go for it.
Did you eat your hat?
Did I eat my... Thank you. So I said, if this thing turns out to be a non-reflective Einstein, I'll eat my hat. Yes. In the talk that I gave in early June, just after we put the paper online, I had that slide, and I did bring my hat with me. And I didn't actually chew it and swallow it, but I at least, I took a bite out of it to the extent. Some people have, I've seen hat cookies, and I've seen hat, pie, baked with a hat crust, and a few other, and people are 3D printing cookie cutters. So if anybody wants to give me hat cookies, I will happily eat my hats. That'd be great.
That's cheating. All right.
Could you possibly make a mirror like the James Webb Telescope from these aperiodic tiles? And that would avoid problems with periodicity, which you get from using hexagons.
Right. So yeah, could you make a mirror, a reflector like the James Webb Telescope? The broader question is, does this thing have engineering applications? And the answer is maybe. It's true that aperiodicity allows you, in some sense, to disrupt repetition, to disrupt the artifacts that you might get in a reflector like the James Webb Space Telescope. So the answer is possibly. Interestingly, though, I would argue that true aperiodicity is overkill for your suggestion, that there are lots of ways to achieve non-repeating structures that aren't aperiodic, and those would probably be sufficient for that kind of application, right? Aperiodicity is a phenomenon that exhibits itself kind of at infinity. But you need an infinitely large structure to know that it never repeats. But we're never going to build infinitely large structures in the real world. And when I'm building something finite, there's in some sense lots of ways to get things that don't have repeated configurations within some bounded region. So the answer is yes, but maybe we don't need to think quite that hard.
Okay, last question.
Hey, great talk.
Thank you.
I don't know if this is a question or I'll make a question out of it, but I was struck by the juxtaposition of the smartest guys in the math room working with tiling, and then you're frantically kind of coloring in patches and hoping you're going to find something that will lead to this proof. And I guess the question is is this unique to tiling, or are there other mathematics and sciences where there's this kind of craftsmanship, this exploratory nature of and I know Roger Penrose was saying in his talk, I could see he was working with transparencies, and he mentioned fiddling with it. And
Yeah.
There's this aspect of using your intuition to make these discoveries. I wonder how you feel about that with tiling.
I love it.
If it's unique to tiling, or
I think it's especially useful in the context of tilings, but I don't think it's unique to tilings. I think there's a beautiful tradition in science, and probably Marjorie can speak to this better than I can, a tradition of model making in order to advance discoveries. And sure, geometry, tiling theory, those are natural opportunities to build models. Even out in the hall here, I noticed there's a glass case with some really beautiful polyhedral models that were built based on the Kundian-Rowlett book. And that's another good example of where people have kind of thought things through by building models. I think there are examples of this in other fields as well. I mean, my expertise kind of dwindles out, but I mean, certainly in chemistry, organic chemistry, we build models in order to understand things. And I think that part of the process of the discovery of the double helix of DNA involved staring at physical models in order to kind of figure out what the structure would have to be. But I might be making that up a little bit. I'm also, right at the moment, I'm reading Paul Steinhardt's book, which he published in 2019, The Second Kind of Impossible, which is about the discovery of quasicrystals and its relationship to aperiodic tilings. And he talks also about the joy of building models. Maybe that's a cheating answer because it's a little bit too close to what we're talking about today.
Okay, well, thank you. Let's thank Craig one last time.